Okay, in this video I'm going to introduce the concept of the Fourier transform in as little time as possible. If you're looking for a more detailed or thorough approach, you should see my website universityphysicstutorials.com. To begin with, I've written the Fourier transform and its inverse on front of you. Note what happens, and I will speak about it more in depth, that we input a function of time, and through the integral transform we get out one of frequency. If we input one of frequency, through the integral transform we get out back one of time. If we put in one that was a function of space in here, we get back out one that is a function of spatial frequency. So we get the inverse of the units of whatever function went in. The bottom line up front about the Fourier transform is that it transforms a function of one particular variable, let's say time, which might be measured in seconds, and this would live in the in the time domain, and it would be transformed into a second function which lives in the frequency domain and would be measured in per seconds or hertz, where the input function was one of time. And also the Fourier transform changes the basis of your function to one of cosines and sines. Another way of looking at it is that the Fourier transform does two things. It gives you a domain change to the frequency domain. So where your input function was one of time, say, your output function will be one of frequency measured in per seconds. If your input function is one of meters, your output function will be one of per meter or spatial frequency. Furthermore, the Fourier transform expresses your function in the frequency domain using cosines and sines as the basis functions. The concept of basis functions shouldn't be new to you, because we use I hat, j hat, k hat in the Cartesian coordinate system to express every point. We also might use spherical polar coordinates, or we might use cylindrical coordinates, all different ways of expressing the same points in the space, and they all have their different uses. Cosines and sines can be used to express points as well, because they are mathematically orthogonal to each other. We know, of course, that physically I, j and k are perpendicular or orthogonal to each other, but mathematically cosine and sine can be shown to be orthogonal to each other, and therefore offer the possibility of using those as a way of expressing every point in your space, namely frequency space. How does the Fourier transform work? Well, if I was to ask you how many cents do you have in €1, you would divide €1 by 1 cent and get 100. You do the same thing to find out that there are 8 8s and 64. So if you wanted to find out how many 6 Hz signals are in your initial signal, perhaps you would divide your initial signal by 6 Hz. Is that what the Fourier transform is doing? Now I have an important aside which I'm actually not going to dwell on. If you require, you can pause the video and read it yourself. Within the Fourier transform integrals, there exists product of cosines and sines, which using clever trigonometric identities can be written as a single cosine. Within the Fourier integrals, any sine components will integrate to 0. Therefore, we can actually add an I times sine to the cosine we found above and integrate it, and it will give us the exact same answer as a single cosine. This allows us to utilize Euler's equation and go from using cosine and sine to complex exponentials. That is the end of my aside. So the purpose of the aside was to show that within the Fourier integrals, integrating cosine is the exact same as integrating a complex exponential, because the sine will always integrate to 0. Therefore, going back to our question, if we start with an initial function f of t, if we divide that by cosine 6t, which is a signal with frequency 6, it's the same as dividing it by e to the i6t, which is of course the same as multiplying it by e to the minus i6t. But this is only computed at one particular point, or valid at one particular point. So if we integrate it for all time, we get the Fourier transform of that particular frequency. Or more generally, we can think of this using the angular frequency omega. Of course, it's easy to switch between the angular frequency and the linear frequency by the factor of 2 pi. Why do we bother using the Fourier transform? Physically, the Fourier transform will tell you the frequency components of your function or signal. This all stems from the concept of Fourier series, which say that any signal, any periodic signal actually, can be expressed as a combination of sines and cosines of varying frequencies. So the Fourier transform is simply extending the concept of the Fourier series to infinity or to aperiodic functions, and will still give you the frequency components of your signal. Mathematically, the Fourier transform often allows you to perform complicated mathematical manipulations in the Fourier domain much simpler than they would be in the original time or spatial domain. We speak of decomposing our function into its frequency components in the Fourier domain. Next, I'd like to show you some Fourier transforms. If my input function is a single sinusoid of frequency 20, the Fourier transform will give me a single peak or a delta function at the frequency of 20 in the Fourier domain. So it will show me the single frequency that was in the input function. This is in contrast to an input square wave. If I perform the Fourier transform of a square wave, I get many frequencies of different amplitudes, and at the higher frequencies we require large amplitudes. The point is that a square wave requires many frequencies in order to fully represent it, whereas a single cosine only requires one. The Fourier transform has decomposed my square wave into its many frequency components. You should have seen during your studies that power series can be used to approximate functions. With an input variable x, you go through your power series and you come out at the value of your function at that particular point in space. Power series, however, only approximate functions locally. The usual power series used in order to approximate functions are the Taylor and Maclaurin. However, we want to expand this to approximate a function globally. Joseph Fourier suggested that cosines and sines inside an infinite series could approximate a function globally. So if you can accept that a power series of the following form is able to approximate your function locally, then you should have no difficulty in accepting that a power series in cosines and sines, or a Fourier series, can approximate your function globally. In Cartesian space, we usually use the unit vectors I hat, j hat, k hat to represent every point, and they have the following orthogonality properties here. They can express every point because they are in fact mathematically and physically orthogonal. As I said earlier on, cosine and sine are mathematically orthogonal and can do the same job. However, in order to represent a point in space, in 2D space, we only require two basis vectors. But if we use cosines and sines, we require an infinite number of basis functions. And I've written them here. We know the cos of naught is 1, the sine of naught is naught, and thereafter we increment the frequency. In the event that you need some convincing, let's look at a square wave. We start off with a single sinusoid of one frequency. We triple its frequency. And thereafter we add many different sinusoids of different frequencies of odd number. What we see is the more different sinusoids of varying frequency we add, the closer we come to properly representing a square wave when we started out with a single sinusoid. The other reason we are interested in using sinusoids as a basis is that their argument must be dimensionless. So where we have an input function of time, let's say, this means that k must be of unit per second. It is a frequency. If the input function is one of position, then the output function, or the k, would be of spatial frequency. So using functions rather than vectors gives us access to the frequency components in frequency space. Also, all differential equations are solved using real and complex exponentials. The Fourier series and the Fourier transform will always be useful therefore in solving differential equations, because the basis will be the cosines and sines, or the complex exponentials. In fact, if we extend this concept to real exponentials, we get the Laplace transform. So that's the relationship between the Fourier and Laplace transform. Fourier transform only uses complex exponentials, the Laplace transform uses both, and as a result it uses both for the solutions to differential equations. Next, I'd like to very quickly illustrate how we derive the Fourier transform. Joseph Fourier showed that all 2 pi periodic functions have a Fourier transform which is given by the following equations. This concept is easily extended to periodic functions of period twice L, as done by this particular equation. As a matter of interest, the expressions here will show you how to go between cosine of omega t and cosine kx, or move in between time and space if you like. So this equation here is our Fourier series using omega instead of the linear frequency nu. The next thing to do is to insert the integrals which will calculate a sub 0, a sub n and b sub n. I have done so here in the equations in the red box. Note that this is a periodic function and therefore I'm giving it the subscript of L. Furthermore, I'm using a dummy variable inside the integrals for an, bn and a0. This use, or this technique, is of great use and will be seen, its importance will be seen later. This equation has discrete components due to the summation, but the discrete variable is omega sub n. Through the definition of omega, we can therefore calculate delta omega, which is omega n plus 1 minus omega n, which turns out to be pi over L. This value for pi over L can be substituted in here and in here. An aperiodic function can be thought of as a periodic function with an infinite period. Therefore what we do is we extend the period of our function to infinity, or let delta omega go to 0. And just like the Riemann sums, the infinite sum will become an integral, and delta omega will become d omega. However, in the integral for a sub 0 there is no summation, and as a result, as delta omega goes to 0, this will simply become 0, and we get no constant term. What we are left with is the following equation on the top of your screen. Note that the integral goes from 0 to infinity, and that we've gone from a sub n and b sub n to a and b of omega. It is important to note, however, that a and b of omega still involve their own infinite integrals. As discussed earlier on in the video, because of a and omega and b of omega, we essentially have a product of cosines in here and a product of sines here, which, as we said earlier on, can be re-expressed as a single cosine. Thereafter, we look at the integral here, which is even in cosine. Therefore, we extend the lower limit to negative infinity and half the answer. This gives us the factor of 2 here. The 1 over pi is a legacy issue from the Fourier series. Finally, using the trick I discussed earlier on in the video, where we introduce the sign which is going to integrate to 0 anyway, we can now incorporate Euler's equation and move from trigonometric cosine and sine to complex exponentials. Note the importance of our dummy variable r, which if it had been left at t wouldn't have allowed us to get to this particular expression. Next, we split the exponential between a positive and negative exponential. We note that each of the I omega t here can be separated out, and we are left with our Fourier transform pair. We can split our Fourier transform pair in 3 different ways, which I've written here. or we can revert back to the linear frequency here. Note that I can move the constant term 1 over 2 pi between the forward and inverse transforms, no problem. So that's all I've got to say about that. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also give a comment on universityphysicstutorials.com.